Hey everybody, this video is going to be a full-blown review on the entire waves unit, including wave anatomy, basics, sound, light, etc. Even though we've already kind of had our IA based on the basics and anatomy and characteristics of sound, we're still going to need a little bit of review in order to move forward with a lot of the content here of this waves unit. Okay, let's start. So we start with this idea that waves are basically carriers of energy. That's how energy could travel from one place to another, through waves. And when you have a wave, you start with a pulse, which is a single disturbance. A wave is essentially multiple pulses happening over regular intervals. So if it's an uneven interval, then it's not really a periodic wave. And then we have what's called the medium, which is the material or matter through which a wave travels. And here we have two types of waves based on that. We have electromagnetic waves, which do not need a medium. And then we also have mechanical waves, which do need a medium. So we started off talking with mechanical waves because they do need a medium, but EM waves, which we kind of summed it up with, they do not need a medium. Okay. And then here we go on to even more types of waves based on the direction of propagation. So one of them we're going to call longitudinal, and the other one we call transverse. One of them is a parallel vibration and the other one is a perpendicular vibration. So usually we represent transverse with our sine curve like this, and then longitudinal with vertical lines to show vibrations. Alright, so here we have a wave, and this diagram here is going to help us show the parts of a wave. So we start with our amplitude, which is basically the height from our equilibrium line. It's never from top to bottom, it's top to the middle or bottom to the middle. That's our amplitude. Then we have the wavelength, which is a measure of a full wave. From here to here can be a wavelength. And we usually symbolize that with lambda. Then we have these two things called the crests and the troughs. Crests right here, the top parts, and troughs are the bottom parts, the low points. You can also measure a wavelength from crest to crest, or trough to trough, or two corresponding points on a wave, like this. When they're corresponding with each other, they're in phase. If they're not corresponding with each other, they're out of phase. You could even have corresponding points over two full wavelengths. For example, from here to all the way over here. That's two full waves going through it. They're still in phase as long as they're corresponding to each other. Alright, so I've talked already about wavelengths. And wavelengths is essentially the length of one full wave. We usually resemble that with our variable lambda. It's a Greek letter. Looks like an upside down Y, kinda. Okay. And usually you could solve for it if they give you a distance of one full wave. So it's usually distance per wave. So in there, for example, if they give you here in our image, we don't have a full wave. We have 1.5. We have 1.5 waves fitting the span of 3 meters. So if we're looking for the span of just one full wave, that's our wavelength, then we got to do essentially this. 3 meters over 1.5 waves to get us 2 meters per wave, which is our wavelength. Okay, frequency now is waves per second. Symbol this with F. So it's usually waves, or you could have cycles or vibrations. That's another way of saying waves. So if you have waves, cycles, or vibrations over the number of seconds. Let me just specify this. So it's more like number of waves over a number of seconds. Okay. As an example, we could say we have 10 waves in 15 seconds. So in order to solve for that, you would do Now let's talk a little bit about some wave behaviors, and we'll start with interference. When waves overlap and superpose, their amplitudes combine in one of two ways. The first one is constructive interference, when you have two crests or two troughs overlapping and their amplitudes add up. So if you have a crest plus another crest, then they make an even bigger whoosh crest like that. Or you could get the same thing with troughs. Like that. Destructive interference is when a crest and a trough overlap and the amplitudes subtract, so they kind of cancel out. It's like a flat line. Now when you have interference happening, then you have what is called standing waves. It involves both constructive and destructive interference happening at the same time. So here I've drawn for you the first four orders of standing waves. So standing waves look like waves that are standing in place. They're not traveling along the medium. And here you'll see the standing wave patterns for the first four orders, first, second, third, fourth. This is what they basically look like. The first order looks like just a single up and down crest and trough. Second looks like a full wave and up two humps going up and down. Third is 3. 4 is, you'll see 4. And this is how the patterns are usually drawn. Notice here, these don't exactly indicate a full wave, the first order. You'll notice that it's almost like half a wave. The second wave is one full wave, third is 1.5 waves, and the fourth is 2 waves. So sometimes you might have questions that ask you, how do I calculate for the wavelength of a standing wave? Usually, they might give you something like this. Let's say this entire span is 3 meters long. Let's say 4 meters instead. From here to here. 4 meters fits an entire standing wave pattern. In our first order, if half a wave fits over the span of 4 meters, that means our wavelength here is going to be 8 meters. Because half a wave only fits 4 meters. Then if you have a full wave, then you have 8 meters. Now our second harmonic here is a full wave in 4 meters. That's a wavelength. Our third one is 1.5 waves in 4 meters. That means a full wave has to stop over here, from here to here. So 1.5, 4 divided by 1.5 is going to equal 2.67 approximately, 2 2/3. And then our fourth harmonic, we have 2 waves fitting the span of 4 meters. So halfway down the 4 meter mark, we're going to see already a full wave. So 4 divided by 2 will give us 2 meters. So notice here, as you progress up the order of standing waves, you'll see shorter wavelengths fitting the span of like the same distance. Alright, now here is another important thing about standing waves. We have to label the parts of a standing wave. So there are two parts called the nodes and the antinodes. Okay, so I'm going to circle for you where the nodes are, right here. These two dots for the first order. Second, you'll see 3. They look like the parts where the wave looks like it's standing still, not moving. The first order, you'll see 2 nodes. Second, you'll see 3. Third, you'll see 4. And fourth, you'll see 5. So you're always going to have one more node for each order, whereas the antinodes are the parts that go up and down. That's where constructive interference happens. Nodes are for destructive interference, where the waves cancel out, and then the antinodes are constructive, where the waves maximize their amplitude. It's right here. So there's 1 for the first, we have 2 for the second, 3 for the third, and 4 for the fourth. So you're always going to have the same number of antinodes as the order. So I'm writing it off to the side for you guys to see. So key things, this is how you measure wavelengths of standing waves. You count the number of waves that fits the pattern, and then you take that distance and divide it by the number of waves. And then here you also need to remember the nodes and antinodes, how to count them up. Nodes are the parts that stand still. You're always going to have one more. You start from end to end. And then the antinodes are the parts that go up and down. They usually match the number of order of the standing wave. Now we get into sound waves. 2 big important facts about sound waves. They're mechanical waves, they need a medium, and they're longitudinal waves that vibrate parallel to the wave's direction of movement. Okay, now certain characteristics of waves translate to different parts of sound. So frequency of a wave is related to the pitch of the sound. So right now my voice kind of sucks, still recovering, so it's a lower pitch, lower frequency. Whereas I normally talk with a higher pitch voice. My normal voice is higher pitched, so it's higher frequency, higher pitch. Okay, amplitude relates to the volume of the sound. So bigger amplitude, bigger energy, bigger volume. And sound also travels fastest in solids. But the big thing you need to remember, this is also on the reference table, is that the speed of sound in air at standard temperature and pressure is equal to 331 meters per second. Now here's a wave behavior that's mostly applicable as a sound, and that's called resonance. And when you have an vibrating object, which causes another object to vibrate at the same frequency, that's typically the natural frequency, then net resonance occurs. And usually what you have as sort of an indicator of resonance is that you see an exchange of energy. You'll see higher wave amplitudes. It becomes also louder sounds. It sounds fuller and louder. So it's a nice, pleasing sound. It's like when you tune in 2 instruments together. If you hit the same note, that's resonance occurring. And you'll see here a louder sound, a fuller sound. Some examples also include musical instruments, blowing air across an empty bottle, the collapse of the Tacoma Narrows Bridge, which I showed in class, as well as sound shattering a wine glass, which I also showed in class. Then we get into light and the electromagnetic wave spectrum. So light is electromagnetic waves. They do not need a medium. They can travel through vacuums. Sound cannot travel through vacuums. Light is also propagates as a transverse wave. And the type of wave, there are different types of waves along the entire spectrum. So spectrum indicates there are different types. And each type is determined by the frequency, which also, I forgot to mention, indicates energy. So the energy carried by an EM wave is indicated by its frequency. So high frequency also indicates high energy. That's why gamma rays are very dangerous. High frequency, high energy. As well as consequently the wavelength. If you have high frequency, you also have a short wavelength. So all these types have the same speed in the same medium. And the speed of light in a vacuum and air is 3 times 10 to the 8th meters per second. That's in the reference table. So speed and wavelength also change, while frequency remains constant when light waves cross into a new medium. So again, the medium determines the speed it has, and as a result, it will also change the wavelength, but the frequency will stay the same. It's really the frequency that determines the type of wave. Same thing with colors. Each color has its own certain frequency range. And usually if you want to have to solve a problem that asks you to pretty much identify what type of wave it is or the color, you have to go by the frequency primarily. Primarily the frequency will tell you the type of wave it is. Okay, so in reflection, waves bounce off surfaces and invert. So this is kind of the same for both sound and light. You have a wave traveling this way, hits a surface, and it comes back the other way. This is kind of relevant in echoes. It's almost the same thing in mirror reflections for light. So a lot of the problems you'll deal with reflection mostly pertain to light. So let's say you have a surface like this, a mirror, and then you have a light ray approaching the surface. Now the angles, we always measure to the normal line. So when you have a surface like this, you got to draw your normal line. So it looks kind of just like this. If your surface is like this, then your normal line will look like that. And we measure our angles with that normal line, so it's right here. We do not measure with the horizontal, like here, with the surface. Never measure to the surface. Always measure with the normal line. So here we come with our handy dandy protractor. So you're always going to use these things, these set of 2 lines. I'm going to show you guys how to measure the angle of incidence. So the angle of incidence is the incoming light ray. So you're going to line up the bottom horizontal line with the surface and the vertical line with the normal. And you'll see here, it lines up with approximately 63 degrees. However, that is with the surface this way. What we need is with the normal line right here. So 90 minus 63, you'll get approximately 27 degrees. So that's our angle of incidence. It's always with the normal line. If you don't want to use the 90 degrees measurement, if you don't want to subtract from 90, then I suggest you do it this way. You have to measure your angle then with the normal line. You line it up this way. And here, if you look closely, again you'll get approximately 27 degrees. Right there, if you measure it that way. So remember, you could do it one of 2 ways. You line your protractor up with the normal line, and you don't have to subtract from 90. But if you line it up with the surface, then you have to subtract from 90. Okay, now going on about the angle of reflection. So if a light ray comes in at 27 degrees, then it bounces off at the same angle, also 27 degrees. So angle of reflection is always equal to the angle of incidence. Now what happens if our surface is like this? Then once again, you have to draw your normal line like this. And your angle of incidence is still with the normal line this time, this way. And your angle of reflection is also, once again, with the normal line this way. If they ask for the angle in between the 2 rays, it's always double the angles. So if we have 27 degrees as our angle of incidence and reflection, then you add them up together and it becomes 54 degrees. That's the angle in between the 2 rays. So what happens when waves have to encounter an obstacle? So diffraction happens. It's when waves bend around or through obstacles and then they spread out. So what happens when they encounter this obstacle, this slit right here? Well, they have to bend through it. And then they spread out like this. And they go out in this direction. They spread out that way. So that's basically diffraction. Now refraction is kind of difficult, I would say. So light, this is only specific to light rays, EM waves. So they change speed, wavelength, and direction when they enter a new medium. If you saw with the other wave behaviors, they only require the same medium. But refraction happens when light travels from one medium to another. So you need two mediums. So light travels fastest in vacuum and air. So I gave both the speed, right here, and the n value. What is the n value? That's the index of refraction. And it's a number ratio that compares the speed of light in a vacuum to a specific medium. And it never goes below 1.0. 1.0 is our smallest n value. And that tells you the fastest speed for light, 3 times 10 to the 8th meters per second. So you're always going to see n values that are higher than 1. So as n goes up, the speed of light will go down. It slows down. If it's fastest at 1.0 and it never goes below 1.0, then our n values have to go up and our speed has to go down as a result. So with speed, also is wavelength decreasing. But frequency stays constant because this frequency helps you identify the type of wave. Okay, so it's inverse relationships between n with speed and with wavelength. Okay, second fact, refraction and reflection happen simultaneously. So you might see diagrams like this. So you have an incident ray coming in like this. It's going to reflect off the surface as well as refract. So you'll see both of these things happen simultaneously at the same time. Then we have Snell's Law, which is used for determining the direction of the change in direction for light rays as it enters a new medium. So in the previous slide, you have n equals c over v to help you determine the different speeds. Snell's Law helps you determine the change in direction now. So you need two mediums, and you need to look up both of their n values, their indices of refraction, n1, n2, and it uses the angles. So you make sure you use the corresponding angles with the corresponding medium. So as an example, let's say we have the boundary between two medium, let's say air and water. Air is usually 1.00 and water is 1.33 for their n values. As always, you need to draw your normal line. And let's say you have an angle of incidence this way. So that's your theta 1. You make sure you measure it with the normal line. If you want to figure out what's the angle of refraction, theta 2, then you use Snell's Law. Or if you're missing any one of these values, if you're given 3 and you're missing one of them, then you can use Snell's Law to figure out the missing value. So make sure you use the corresponding values. So theta 1 goes with 1.0, theta 2 goes with 1.33. And make sure you know how to use the protractor, guys. Always measure with the normal line. You can do it one of two ways. Measure the angle with the surface, and you have to subtract from 90. Or if you measure it with the normal line, you don't have to subtract from 90. Okay, so when you have a light or sound source and an observer, either one or both must be moving in order for the Doppler effect or the Doppler shift to be observed or to happen. So usually if you have something that's moving towards either the observer or the sound source moving towards each other, then you're going to see a sort of compression of the waves. It sort of compresses and moves towards and it compresses and shortens these waves. So the wavelength shortens and it goes down. As a result, frequency goes up. Further away, if it moves away, then the waves elongate, they stretch out, so they increase in size. Whereas the frequency has to go down as a result. Now, it might sound differently then. So it's a higher pitch for sound, and it's a blue shift. because blue has a higher frequency for the colors. For the away, it's a lower pitch, and it's for light, it's a red shift because red is a lower frequency. Okay. And that's the end of the video. I hope you also have checked out the waves practice test. I put up that video much earlier than this one, so I hope you've seen that one first before going to here. Use this video to help you go over the content, or you might want to watch this video first before going over the practice test, but I highly suggest you focus a lot more on the practice test and use this to supplement your knowledge. See ya, guys.